All right, so Chemistry 3101, this is section 7.9, and we're going to now look at unimolecular reactions, SN1 and E1 reactions. We've already spent quite a bit of time talking about SN2 and E2 reactions. So we're going to start off by taking a look at a reaction. It says right here off the slide, it says, consider this reaction where substitution and elimination products are both formed when you dissolve tert-butyl bromide in ethanol. So you literally just put the compound in a solvent. Ethanol is the same old ethanol that's found in alcoholic beverages, and you actually end up with two different products. You end up with a substitution product where you substituted the ethoxy group for the bromine, that's one, and you also do an elimination reaction where you make this compound called isobutylene. Now, what's different here from what we saw in SN1, or sorry, in SN2 reactions, in E2 reactions rather, was that we have a tertiary substrate, right? When we talked about SN2 reactions, we never talked about tertiary substrates. We always talked about methyl substrates and primary substrates. So just reading off the slide, it says, since the substrate is tertiary, SN2 is impossible. Can't happen. Also, the reagent is ethanol, which is not a strong base. So E2 is probably not going to happen. Remember, all these E2 reactions that we've looked at, they either involved, ethoxide or tert-butoxide, but we had to have a strong base in order for those to occur. So what's happening here? It turns out that the formation of the substitution and the elimination products actually follow a first-order kinetics, which proves that it's not an E2 and it's not an SN2 reaction. So what does first-order kinetics means? It means that our rate law looks like this. Our rate is going to be equal to the rate constant multiplied by only the concentration of the substrate, right? The concentration of the solvent or whatever, it has nothing to do with it, okay? So we're only going to consider the concentration of the substrate in a first-order reaction. So when we have the substitution reaction, we call it an SN1 reaction. And when we have an elimination reaction, we call it an E1 reaction. Now, what's the first step in this SN1 or E1 process? Now, the way I think of it is SN1 at a time, right? E1 at a time. So it means there's two steps and they occur one at a time. The first step is the ionization, which results from the loss of a leaving group. We lose bromide and we end up forming a carbocation. Now, this is the rate determining step, and we're going to look at that a little bit more later on. But think about it. If you end up forming a tertiary carbocation, it can actually undergo the substitution to give us the SN1 product, and it can also undergo elimination to give us the E1 product. Now, what's that all going to look like? And we're going to investigate that over the next few slides. So it says here, since the substitution reaction, rather, of the tertiary substrate in an alcohol solvent like ethanol proceeds through this two-step mechanism. Again, every time we're dealing with an SN1 or an E1 reaction, in this slide we're just focusing on an SN1, but every time we have one of these reactions, these first-order reactions, the first step is always the loss of leaving group. Again, this is the rate determining step of the reaction, the loss of leaving group. Then, if you want to do the substitution reaction, you've got a nucleophilic attack by the ethanol in this case. Then you have to have a proton transfer in order to complete the process and form the substitution product. Again, the last step is just a proton's transfer. All right. We call this reaction a solvolysis. The reason why is because the nucleophile is the solvent, right? You're just dissolving the compound in ethanol, but ethanol is actually doing the reaction itself, right? If you think about SN2 reactions, the solvents that we use, whether it was acetone or DMSO or HMPA or whatever, none of those solvents are going to be involved in any of the SN2 or E2 reactions, right? So we call this solvolysis. It's a term you'll hear me say once in a while, solvolysis. If we take a look at the reaction coordinate for an SN1 reaction, this is what it looks like. You can see there's actually a couple of steps involved here in the SN1. Again, we have a proton transfer in solvolysis, but that's technically not part of the overall SN1 because sometimes we don't have the proton transfer. But again, I keep referring to the loss of the leaving group as being the rate determining step, right? It's the step that determines how fast the reaction is going to go. right? The formation of that carbocation intermediate, remember these are transition states here at the top, the maxima, but the minima are intermediates, and the formation of that carbocation intermediate, that proceeds through the highest activation energy or the highest energy transition state. So that's something that you need to know. I remember a number of years ago, there was an ACS final and they asked that question. I don't remember exactly how it was asked, but students are expected to know that the first step, the rate determining step, is going to be the loss of the leaving group to form the carbocation in an Sn1 reaction. Important that you know that. Just going back to the kinetics, going back to the rate law. And this is kind of rehashing a little bit of stuff that we already know, but bringing in some new things here. Since the formation of that carbocation, the reaction rate, right, the rate of the reaction only depends on the formation of the carbocation. Well, what does that depend on? It only depends on the substrate, nothing else, right? So that explains why the reaction is first order. Again, I'll repeat myself. I go back here. If the rate of the reaction only depends on this step, right, going from here to here, well, what does that depend on? It only depends on the starting material. That's it. So that's why it's a first order. That's why we can write the rate law as being equal to, the rate is being equal to K multiplied just by the concentration of the substrate. That's it. That's first order kinetics. So when we see Sn1, what does it stand for? Well, Sn hasn't changed from Sn2. S still stands for substitution. N stands for nucleophilic, but the 1 means that it's a unimolecular or a one at a time. And again, that first step, the formation of the carbocation, is the rate determining step. You see how it all goes together, right? If it's an Sn1 and it's unimolecular, right? That's what the 1 stands for. Well, of course, it's only going to depend on the concentration of the substrate, right? That's it. Okay. Again, this is just a generic version of the mechanism here. So the substitution reaction that occurs stepwise first involves the formation of this carbocation intermediate followed by the nucleophilic attack. Now we saw when it was solvolysis, when we used an alcohol as our nucleophile, there was a proton transfer right at the very end. It's not shown here. We're assuming that the nucleophile has a negative charge, okay? But again, it's the same generic mechanism over and over whenever we look at an Sn1 mechanism. Now, what about the E1 reaction, right? We've covered the Sn1, and there's some more details that we're going to get into regarding the Sn1 in a little bit. But what about this E1 reaction? How does that work? Well, let's think about it. If my first step is the loss of leaving group and I form a carbocation, right? If I consider this an alpha carbon, so to speak, well, then, I mean, there's 3 beta carbons that are all identical. But if I just look at this one here, I just choose one, okay? And I know that there's 2 more protons here. Yes, there's another one, and yes, there's another one. We're just leaving those out. This is just for instructional purposes only. But in order to form that alkene, to do the elimination reaction, I just have to remove a proton, right? Again, which is a 2-step process. So here, the ethanol is behaving as a base and not a nucleophile in order to deprotonate the carbocation and produce an alkene. Again, the E1 reaction mechanism is unimolecular, right? The first step is the same. It's just the loss of leaving group, and that only depends on the concentration of your substrate. Therefore, again, it's a unimolecular reaction, follows the same old first order kinetics, right? And if I look at the kinetics, and if I compare the products that are formed from the E1 and the Sn1 reaction, E1, again, E stands for elimination, 1 stands for unimolecular. Well, the rate determining step is identical, right, for both of them, whether I'm doing the E1 reaction or the Sn1 reaction. The difference is in the activation energy that produces, the Sn1, which is, or the substitution product, which is going to be more stable than the E1. Why? Because the E1 has an alkene, and a pi bond is weaker than a sigma bond, so we end up with something that's more stable here. So it's going to be more thermodynamically stable. Okay, it's the thermodynamic product. Anyhow, and it's also the kinetic product. But you see that the difference in relative energy isn't all that great between our Sn1 and our E1 product, is it? Right? It's not. There's not a huge difference there, and we're going to talk about that a little bit more. Now, before we talk about, how do I know if I get the Sn1 product, or how do I know if I get the E1 product, since they both have the same starting material? They both have the same rate determining step, right? The formation of the carbocation. Before we do that, I want to talk about carbocations with you for a second. Right? I want to take you back to earlier in our class when we spent some time looking at what? Nucleophilic attack, loss of leaving group, proton transport, and carbocation rearrangements. I don't know if you remember this, but one of the statements that I made in class when we were discussing carbocation rearrangements, right, the old RGT as we use the acronym to describe it, I told you that if a carbocation can rearrange, it's going to. Okay? The same thing applies in an Sn1 or an E1 mechanism. Let me show you what I mean. And these are just very specific examples. Right? But if you take a look at what's happening here, here we're taking this secondary alkyl halide, we have it in water, and we're heating it up. Now, we're not going to get an Sn2 reaction. This is a weak nucleophile. We're not going to get an E2 reaction. This is not a strong base. So the products that we get would come from a first order reaction. And we see that we actually get two different substitution products where we replace the bromine for a hydroxyl that comes from the water. Now, remember, the first step is the loss of leaving group. Okay, I'm just going to draw what would happen after we lose, after we lose the bromine. I would end up with a secondary carbocation. Well, hold the phone. There's also a proton here. And that proton could do a hydride shift to give me what? I'd end up with a tertiary carbocation. Let's draw that tertiary carbocation. It's going to look like this. So what you see is that I can get substitution occurring at this position to give me this Sn1 product. And I can also get substitution occurring to give me this product, which comes from that tertiary carbocation. So we end up with two different products, and we also get some elimination products, which we're not going to discuss at this second. But again, the whole idea is this: how do you justify this product? Where the hell does that come from? Pardon my language. When you form that tertiary carbocation, or secondary carbocation rather, if it can rearrange, it's going to give you something more stable. We could practice, the concept on the next one. Look, we lose our leaving group. What would we produce? We'd produce this carbocation right here. That's a secondary carbocation. But we know that we could do a methyl shift in order to give us this carbocation. So we have this guy right here where we have the positive charge here. Again, I'll use the yellow highlighter. With the secondary carbocation, once the substitution occurs, I'm going to end up with this product. But on the tertiary carbocation, I'm going to end up with this product after substitution. So again, what's the bottom line? The bottom line is, if a carbocation rearrangement can occur to give you something more stable, what's the answer? It's going to happen. So you end up with a mixture here. You end up with mixtures. Look, you end up with two alcohols here, some elimination products. You end up with two alcohols here and some more elimination products. I don't want to take anything away from Sn1 and E1 reactions and say, oh, they're not important, because they're important. Otherwise, I wouldn't be talking about them. You need to understand these mechanisms. However, I want you to just think in terms of synthetic utility. How useful are these reactions, right? With Sn2 and E2 reactions, we can control things like Regio Selectivity. We can, make substrates that are chiral, and so that we get, stereospecific reactions. What you're going to see, and this is a recurring theme with unimolecular reactions, is that we end up with a host of products. Okay. Now, are there some times when an Sn1 or an E1 reaction can be useful? Absolutely. Absolutely. We don't want to throw the reaction out and say it's not useful. I just want you to understand that it's more difficult to control and you end up with more products. Well, let's take a look at a real cool exception. Like I told you before, I know I repeat myself a lot, that as one of my students so aptly put it a number of semesters ago, organic chemistry is learning a whole bunch of rules and then all the exceptions to those rules. So there's kind of an interesting exception here. This might be worth, what's on this slide right here, you guys, might be worth the value of one multiple choice question on a quiz. I would never ask this on an exam because, it's kind of just a one-off thing here. But it is cool, and it's one of those slides that kind of just proves to you why understanding concepts in organic chemistry is so much more powerful than memorizing stuff. So check this out. Sn1 reactions, you're forming a carbocation. Now, if I was to tell you you've got a primary substrate, is that going to react by an Sn1? You'd probably say, well, no, that's not going to happen because it's primary. Primary carbocations are really unstable. You would never, don't write this down, okay? I actually feel crummy doing this. I feel like I'm a bad person. Okay, this would never, ever happen. You would never form a primary carbocation like that. Bad carbocation. In fact, so I'm going to erase all that. I'm not putting that up on YouTube, but or I'm not leaving it there. The permanence of the writing. Okay, but what we actually see is if you take this primary alkyl halide, you put it in just water, you actually get a substitution. Okay, you actually make a substitution product, right? Think about it. It's not an SN2 reaction. It's not a strong nucleophile. You're not going to get an SN2. So it must be an SN1 product. Well, how in the heck can you rationalize that? You can guess that the answer is on the slide here. Now, you can tell that there's some kind of rearrangement that occurred. And so what happens is that you get the loss of the leaving group, kind of like the loss of the leaving group and the carbocation rearranging all at the same time. So you get the 1,2 methyl shift and the loss of the leaving group all occurring simultaneously so that you end up with a tertiary carbocation. Water can come in as your nucleophile. I'm sure that all of that was deleted now that I spent so much time writing it out. Oh, yeah, it's gone. Anyhow, so you get your loss of leaving group and your carbocation rearrangement occurring simultaneously. Then you get the nucleophilic attack, then a proton transfer in the end. Now, I understand that you're learning the subject and you're kind of inundated with material and you're like, oh, it's just a reaction after reaction. But it is kind of cool. And it is one of those very specific examples where it shows you, just a little bit of understanding helps you to understand why you get a substitution product here. But again, I think it's one of those things that unless I showed it to you in class, you would never anticipate it, right? You have to be shown it just like I was when I was a student. I had to be shown it too. All right, well, let's talk about solvents. Do you remember in SN2 and E2 reactions how we talked about polar aprotic solvents, or I think the book just called them aprotic solvents, like acetone. What else did they have? Acetonitrile, HMPA, DMSO. They said these are the best solvents for an SN2 reaction. Why? Because they could stabilize a positive charge of a cation, but they couldn't stabilize an anion, right? And so it rendered the nucleophile more reactive. Well, what we see with SN1 and E1 reactions is the exact opposite. Okay, we see the exact opposite effect. We see that the more polar a solvent is, so polar protic solvents like water, methanol, ethanol, these are going to be the types of solvents that will promote the reactivity of an SN1 or an E1 reaction. So a tertiary substrate, for example, like let's say we have terbutyl chloride, it's going to react a lot faster in something with a high dielectric constant. Remember, I never would ask you to evaluate a dielectric constant, but you know the higher the dielectric constant, the more polar the compound is. So the more polar the solvent is. So most polar solvent, least polar solvent. So again, the reason why is because a polar protic solvent can both stabilize an anion and it can stabilize a cation. So that renders or that facilitates the loss of the leaving group because we end up with the carbocation being stabilized and the anion stabilized. And again, that just renders, just increases the rate of the reaction because everything's more stable. Okay. Now, if you're not 100% sure about this, if you're like, can you compare this to SN2? Yeah, I can. Okay. Because it's not comparing apples and oranges, but we kind of look at it from a little different point of view. Okay. So what I taught you in the section about SN2 reactions, as I said, a polar aprotic solvent, what it does is since the polar aprotic solvent can stabilize a cation, like a sodium cation or a lithium cation, it can stabilize carbocations, but it can't stabilize an anion. Okay, so a nucleophile is an anion, right? If I write down nucleophile, or a good nucleophile for an SN2 is an anion. So what it does is it doesn't stabilize it, so it raises the energy of the nucleophile. Okay, it just renders it more nucleophilic. In terms of Sn1 reactions, it's a little different, right? Because we're not talking about the reactivity of the substrate. We're talking about the pathway, okay? You see how the pathways are different, right? Here we're talking about the reagent, the actual nucleophile. Here we're talking more about the pathway, okay? And the pathway that leads to the carbocation, right? Because this is the carbocation. This is the loss of the leaving group here, loss of leaving group, and then this is the carbocation that's formed here. So you can see that when you do a Sn1 reaction in a polar protic solvent, what it does is the protic solvent, like water, right? It could form, a hydrogen bond, let's say, and it can stabilize that carbocation. So all the protic solvent can do differently is that it can stabilize the cation and the anion, and therefore it lowers the activation energy to produce the carbocation intermediate. So you see how it's a little bit different, but the idea is still, the same. Okay. Now, am I going to ask you to draw a reaction coordinate diagram? Probably not. But I would ask you to recognize what the heck is going on here and what the heck is going on here. And I can tell you right now that if I was to go up to any of my students who are taking organic chemistry 2 right now, what they would probably remember the best is that when they're doing an SN2 reaction, they want to use a polar aprotic solvent. And when they're looking at an SN1 reaction, they would choose a polar protic solvent. You can imagine this is the kind of thing we could sit here and talk about all day long, but that is really the bottom line on what you need to know. A couple more things we have to take into consideration in section 7.9. What about the leaving group, right? Because the first step of an SN1 or an E1 mechanism is the loss of the leaving group. Well, you can imagine that the ability of the leaving group to leave is going to affect the rate of the reaction. So the better leaving group we have, the weaker the base. You could call it that, or you could say we're looking at the conjugate base of the strongest acid. That's going to be a better leaving group. So you see the iodide is the best, right? Then you go to bromide, then chloride, then HF has a pK of like 3 and something. So fluoride is not going to make a very good leaving group. And there are other leaving groups that we'll look at later on in this chapter. We'll look at them today. But there you go. The rate determining step for an SN1 or an SN2 depends on the formation of the carbocation, but also the more stable the halide, the faster the ionization, right? So, we're taking all these factors into account. And there's one more thing we have to take into account, and that has to deal with carbocations. And there's nothing new here to you. You've all studied resonance structures, right? We spent a lot of time talking about those, and we talked about the stability of carbocations. So it probably wouldn't come as a surprise to you that there are some primary and secondary alkyl halides, that the solvolysis of a primary or secondary alkyl halide would be really slow. However, if you have a benzylic or an allylic halide, they will undergo a solvolysis, which is an SN1 reaction, at a practical rate, thanks to the stability of their carbocation intermediate. What's being said? We already covered tertiary carbocation, but let's say you had this compound, okay, CH2Br. Now, if I was to just tell you, what the heck is going to happen here? This compound is a primary alkyl halide, right? It can undergo an SN2 reaction, no problem. But what it's saying is if you just put it in a polar protic solvent, like water or ethanol or methanol, it can undergo solvolysis. Why? Why can it do it? Because it can spontaneously, well, not spontaneously, but it can lose the leaving group under the proper conditions. Why? Because you end up with a resonance stabilized carbocation, right? The same rationale applies here. If I was to just tell you, okay, you've got this compound, can this undergo an SN2? Hell yeah, right? Absolutely it can. But it could also undergo solvolysis, which is an SN1, right? Why? Because you can lose this leaving group because you end up with a stabilized carbocation. Those are very specific examples, but you're expected to know them, okay? And you can imagine, how am I going to sort all this out in my mind? How would I sort all this out in my brain? There's a lot to sort out here. Well, the more practice that you do, the more that the concepts will start to crystallize in your mind, and it will become even easier and easier to predict, what the heck is happening. So let's say we look at something like this, substrate right here. It's a benzylic substrate, right? This is the benzylic carbon. It's got a leaving group on it. Bada boom, bada bing. So you should be able to judge whether or not a given alkyl halide can undergo an SN1 or an E1. Okay. In general, when we have a primary or secondary alkyl halide, it's only going to undergo solvolysis if it can make some dandy carbocation, right? So why can this undergo solvolysis? Right, you think about it, you just put this compound in water and stuff happens. Well, yeah, it can, because this leaving group can leave and you end up with a benzylic carbocation. And you could practice drawing all the resonance structures there, but that's the bottom line. So again, it is logical, but there are some thought processes involved in solving these types of problems. All right. Now, in terms of regio selectivity, so that's the title of this slide, is E1 regio selectivity. When we looked at E2 eliminations, we saw that we could form regioisomers based on whether we used an unhindered base or a hindered base, and we said, yeah, that's great, and we kind of celebrated it or whatever. Well, if you're doing an E1 reaction, right, remember the first step here is loss of leaving group, and you would end up forming this carbocation. Well, you have beta protons here. If you eliminated that, you'd get this product. You have a beta proton here. That would give you this product. Well, what you would get is a mixture, but the golden rule with E1 reactions is that you always give the most stable alkene as the major product. Okay, 100% of the time. Okay, so that's kind of a golden rule. Right, we saw that with E2, it didn't work that way. It depended on the base, right? It depended on the substrate in some cases when we looked at cyclohexanes. So the thing is that E1s are regioselective, and that you always make the Zaitsev product is the major product, and it would be Zaitsev that's the least hindered. But anyhow, the problem is you can't control it. It's really, I can't even think of a way to control it. I mean, you could fiddle around with solvents or something and see if you get different yields of E1 products, but there's no quick way to control it. So it's not really as useful. So what I kind of alluded to on the last slide is I said, okay, well, if you take this tertiary, alkyl halide, you lose the leaving group, right? You would form this carbocation. So let me just draw it out here quickly. Okay. You have beta protons here. That would give you this product. But then you also have beta protons here. That would give you this product and this product. You see that one of them is a E product, or you could call it a cis product. And then this product is the Z product. And you could also call that a trans. That's a good question, right? You could ask a friend, can a compound be E and be cis at the same time? And this compound is E and cis. I'm kind of stopping here for a second. But check it out. This is an entgegen compound, opposite, right? Because this group is the highest priority. This group is the highest priority. But check it out. These two methyl groups are identical, so they're cis. So this is E and cis. And this one is Z, right? Because the two major groups are on the same side, but it's also trans. I think we asked that question to somebody in a job interview once. I'm talking about at UCCS, somebody who applied for a job teaching, and we said, hey, can an alkene be E and cis or Z and trans? And then can you give me an example? There's an example right there. Anyhow, what was I talking about? Yeah, but the thing is that the E1 product, you're just going to go with the least hindered product, right? So this one is the least hindered, and so it's going to be the major product. So, man, oh man, if something can drive you nuts in organic chemistry, it's the fact that, solvolysis of this alkyl halide can just give you so many different products. Okay. E1 reactions are stereoselective, but realize a mixture of all possible products are going to still be obtained. Man, that's a lot of different products. Anyhow, let's talk about the stereoselectivity of an SN1 reaction. It says that when the alpha carbon in an SN1 is chiral, you get two substitution products that have opposite configurations. So think about this. You start out with a chiral carbon, okay? You lose the leaving group, you make an sp2 hybridized carbon, right? Remember that I told you that a carbocation was like it had was like it's a trigonal planar, right? So this is trigonal planar. That means it's as flat as a pancake. So which side is the nucleophile going to attack? You know, it can attack either side. Attack either side. It's not going to discriminate. There is a small discrimination, but it's in the book talks about it very briefly, but it's so small that I would never ask you about that. You should just know that you're going to get both products. What's crazy about this, so if you're wondering, you know, like, what's the point? Why do you explain this stuff to me? And, you know, well, think about it this way. Making a chiral compound in organic chemistry is tough. Okay, it's very tough. Okay, it takes a lot of time. Can you imagine if you spent, you know, months or whatever working to make a chiral compound like this, and then you throw it in a reaction without understanding what's going to happen? Okay, you just lose the leaving group, and then you end up with, you know, a racemic mixture of products. You would be like throwing stuff, or at least maybe I would. I wouldn't be very happy about that. Okay, I'd get kind of ticked off at that. So this is why you want to have a firm grasp of what the heck is going to happen when you look at a substrate. Okay, well, let's take a look at some problems here. This is question 7.33. It just says draw all of the expected products for each of the following solvolysis reactions. Remember, a solvolysis is a unimolecular reaction. It's a first order reaction. So first order. Since this is a tertiary alkyl halide and we're just putting it in water, remember, we're not going to get an SN2. It's too hindered. Water is not a strong nucleophile. It's a weak nucleophile. But it is a polar protic solvent, so it can stabilize a cation and an anion. So we get a loss of leaving group as our first step, and we form a tertiary carbocation. We also have the chloride. I'm going to leave that out because that's not going to participate in anything to do with the solvolysis reaction, but we've got a beautiful tertiary carbocation now. So what can happen? We can get the water coming in as a nucleophile. So there's no reason why this water couldn't come in as a nucleophile. So we could get a nucleophilic attack followed by a proton transfer. And that would make what? That would make a tertiary alcohol. So we'd end up with this tertiary alcohol. Okay. There's no stereocenter to even be worried about. We could also get elimination. Right? There's two types of beta protons. There's these beta protons here. There's these beta protons here, right? There's two here as well, but there's symmetry here. So if we pulled off the one in red, we would end up with this compound. We have the double bond here. And if we pulled off the one in green, we would end up with this compound like that. Out of the two alkenes, can anybody tell me which one would be the major alkene? Would it be the green one or the red one? I told you there's a golden rule with E1 reactions. Yes, thanks, Bruna. Absolutely. This one will be the major because it's the most substituted, so that's the golden rule. And those would be all the different products that you could form. There's going to be no carbocation rearrangement to worry about because it's tertiary, you can't rearrange. And there you have it. There's no stereochemistry to worry about. Let's take a look at the next one. Again, if you're wondering, you know, Mr. Dion, how do you know what's going to happen? How do you know what's going to happen here? Again, let's just look at it and see if we can evaluate. I mean, I know the question tells us that it's a solvolysis, but think about it. We got a tertiary substrate. It's not going to be an SN2. It's not going to be an E2. Impossible. Okay, this carbon's too hindered for a nucleophilic attack. Okay, we're in a polar protic solvent. We're just heating it up. It's not a strong nucleophile. It's not a strong base. Why would you get an E2 or an SN2? So the first step is going to be the loss of a leaving group. And look what happens. You go from a chiral center. So this is chiral, right? But let's draw what you end up with, the carbocation. You end up with a carbocation that looks like this. So there we go. Now you've got your methyl group and you've got a carbocation. Your chiral center that was here is gone. Bye-bye. It is gone. Forget about it. It's over, right? Because now you've got an sp2 hybridized carbon. It's trigonal planar. So that means that when we're talking about the nucleophilic attack of the solvent, so if I draw some electrons on here, that means the nucleophile can attack from the back face of the molecule or it could attack from the front face of the molecule. So after the proton transfer, you're going to get two products, right? Now, we could just write, I'll just write one of them, and then I'll put plus an enantiomer. I think is probably the easiest way to do it. But I'm going to end up with, my methoxy group here, okay, and this, and I'll put plus an enantiomer. So again, I end up with two enantiomers there. In terms of beta protons, I've got beta protons here. I've got a beta proton here. I can pull off either one, okay, either one. If I pull off the one in red, I'll write the product down here because I'm going to run out of space. But if I pull off the one in red, and I know you could all draw this faster than me, but you end up with this guy. But if I pull off the one in blue, since there's free rotation around this carbon-carbon bond, I end up with two stereoisomers. Let me prove it to you. If I pull off the one in blue, one of the stereoisomers would be this. So you end up with the two methyl groups being cis to each other, but I'm also going to end up with another product where the two methyl groups are trans to one another. So I end up with that. All right. Well, the one where the two methyl groups are cis, this is actually the E compound, and then this one is the Z compound. So you got three alkenes and two ethers that you've made. You've made 5 different compounds from this one substrate. Okay. Could anybody tell me which one of the alkenes would probably be the major one? It's not a trick. Excuse me. What would you answer? You're right that it's one of the blue ones. Yeah, absolutely. It would be the E one, right? It would be the blue one, correct? You're 100% correct when you said blue. And it's the one that's the E isomer. Why? Because it's going to be less sterically hindered because you've got a proton. Come on. Cooperate. There we go, because I've got a pen here. All right, I got my big old phenyl group next to the hydrogen, whereas here it's next to a methyl, so it's more sterically hindered, and that's the reason why. So this would be your major product. Okay, so what I was hoping is that by, me kind of explaining it to you step by step, and I know we're just learning it, that you would see, okay, I'm going to evaluate my substrate, my reagent. It's going to be a solvolysis. I make a tertiary carbocation. It's trigonoplanar. The methanol can come in and attack either face of the molecule. I get 2 enantiomers. I got 2 beta protons, 2 types of beta protons, I should say. And I can end up with the E and the Z since there's free rotation around this bond. Okay. And there you have it, man. You get 5 different compounds. But you see, don't get intimidated by it. If you just take it, one step at a time, just kind of slowly take a peek at it and take another glance at it, you'll always be able to figure it out. All right. So we skip the next section, which deals with kinetic isotope effects. I will never ask you a question about that on your quiz. It's not covered on an ACS final. I've looked at all kinds of, DAT studied materials, the DAT destroyer. I've got DAT flashcards in my office. I don't have any MCAT prep materials in my office because I gave them all away, but I've looked at them and I've never seen them ask a question about this. I've never seen it come up on an ACS final. I've never asked about it. So if you want to read it, it's really quick, very quick, but it just has to do with the kinetics of the reaction and using deuterium. And anyhow, so you could take a look at that, but we're going to skip this section.